Hi, this is Lan. I'm a PhD student from UT Dallas. My presentation is about incorporating spatial correlation into house sale price prediction using a random forest model. Machine learning algorithms have been commonly used to describe house prices in the literature. The most frequently used algorithm is artificial neural network. Many scholars argue that this algorithm can describe and predict house prices more precisely than some traditional statistical models. Support vector machine is another algorithm that have been frequently used, and one suggests that it can perform better than an ANN, which may only converge on a local optimal. The other commonly deployed machine learning algorithm includes decision tree and random forest algorithms. Decision tree can furnish an effective method to identify significant factors for house prices using a build tree. The random forest model essentially is an ensemble of decision trees. It can allow a nonlinear relationship between house price and covariance. However, house prices tend to be spatially autocorrelated, mainly attributable to the shared locational amenity of houses in the same neighborhood, and also because of the similar physical characteristics of adjacent houses. In the literature, a collection of spatial statistical models have been utilized to accommodate spatial correlation in house prices. For example, spatial autoregression model, geographically weighted regression model, and spatial multi-level models. To date, a lack of studies incorporate spatial correlation in machine learning algorithms for house price predictions. In this research, we incorporate proxy variables that are designed to address spatial correlation in a random forest model to describe and predict house prices. And we propose three different types of proxy variables. We would like to evaluate and compare the capability of each of these type of proxy variables in accounting for spatial correlation. And we are interested in accessing the importance of included house price factors. The house price data was collected from the Department of Tax Administration of Fairfax County, Virginia. It contains more than 8,000 single-family house sale records in 2016 and 17, respectively. We used the 2016 house sale data to train the random forest model, and the 2017 house sale data was reserved as testing data. A global Moran's-I test of the 2016 house price data indicate the presence of significant spatial correlation with Moran's-I z-score 81.04. The map, this map shows the hot spots and the cold spots of the house prices in 2016, and we can see hot spots cluster of high house values in the northeastern areas, and the cold spots in some north areas and south areas. To describe house prices, we collect 11 variables which have been commonly appeared in the literature, with 8 of them are numerical variables and 3 are categorical variables. This table provides a summary statistics of these variables. We include 3 different sets of proxy variables to explain spatial correlation that fail to be captured by the covariates. The first set are the geocoded XY coordinates of individual houses. And the second set are the local spatial correlation indices based on the 8 numerical variables. And we include 8 local spatial correlation indices based on the local Moran's-I test, and another 8 based on the local G statistics. And the third set is a collection of buffer distance layers based on the Euclidean distance from individual house. And ideally, we can generate one buffer distance layer for each of the house that measure the distance from all other houses to the target house. However, since the house that sold in 2016 and 17 are not identical, so we generate the buffer distance based on the centroid of the block groups. The map on the left shows the centroids, and the right is an example of the generated distance layers. The random forest model is an example of decision tree with a tree-like structure, and each leaf node represents a classification or decision. Each internal node represents an attribute test. To construct multiple trees, a bootstrap technique is used to draw random samples with replacement from the original training data. And so a tree can grow on each of the samples with randomly selected input values. So suppose there is a housing price training dataset denotes as S, and K different random samples denotes as SK, and then the final predicted house prices can be computed with these formulas, where which is an average of the predicted value of each tree. Local spatial correlation statistics is used to identify local hotspots and geographic outliers. The two most commonly used local statistics include local Moran and local G statistics, and they are slightly different. Local Moran tests only consider neighbors' value, and it excludes the value of the spatial units that being studied. However, the local G test consider all of the values. The random forest model was implemented in RStudio, and we set the parameter number of trees to 150, number of nodes to 5, and R square value shows that the pure random forest model explains around 67% of the variation in house prices, and R square increased to 0.781 in the random forest model with distance layer, which is highest value. And also the prediction error value also indicate that the random forest model with distance layer performs the best. These two plots shows the importance of the included covariates. The left-hand side one is for the random forest model, and we can see the most important variables is living areas, which is substantially more critical than the second most important variables, number of 4 bedrooms. And the 3 categorical variables remain are the least important factors. On the right-hand side plots, we can see that the included XY coordinates are very important. They are ranked the second and the third most important variables. For the distance layers variables, there are some of them are very important, like the layer 63 and layer 22, and the rest of the layer distance variables are generally more important than majority of the covariance variables. The mid and the right plots shows that the local spatial correlation indices variables are generally less important than the their corresponding source attributes variables. For example, the spatial correlation indices variable based on the living area is important, but it's less important than the living area variables. These four maps portray the four most important distance variables, the 63rd, 21st, and 20th, and 18th distance variables, and each of them displaying prominent clusters. And with the top two, they are highly likely to capture the hotspots that we observed in the northeast areas, and the 20s are highly likely to capture the cold spots in the south areas, and then 18s may explain the cold spots in the north areas. These two maps portray the residuals of the random forest model on the left and the random forest model with distance layers on the right. And we can see that the residuals on the left shows prominent spatial correlation with more anxiety z-score 11.63, and this spatial pattern become insignificant on the right. And the reduction, this reduction may suggest that the included distance layer variables successfully account for spatial correlation in the house price data. These scatter plots are displaying the correlation between observed and predicted house prices in 2017. The correlation statistics is 0.82 for the random forest model, which means the pure random forest model generate relative good prediction outcomes. And the correlation statistics slightly increase at the bottom for the random forest model with the local spatial correlation indices. And R statistics increased to 0.71 for the random forest model with XY coordinates, and to 0.72 for the random forest model with distance layer variables. So this research incorporate spatial correlation with proxy variables into the random forest model for house price predictions. And we can see that local spatial autocorrelation variables improve the training and testing results to some level. However, their performance highly depends on the selected covariance variables, and we believe that it may function better when more relevant covariance included in the model. And second, coordinate variables perform very well, and this may attributable to the well-matched spatial pattern between the coordinates variable and the house prices variables. However, the effectiveness of this type of proxy variable may vary from case to case. And the distance layer variables perform slightly better than the coordinates variables because of the similar reason. But we believe this type of proxy variable furnish a better choice because we can generate distant layers from each of the house location or centroid, and it's highly likely that some layers out of all the generated layers can have similar spatial structures as the house price variables. The random forest model have been considered as a black box functions similar as ANN because it doesn't provide much insight of the structures. However, the random forest model that implemented in R reports that the importance of variables and also model performance statistics. The importance plots provide information for us to evaluate those factors, and the results indicate that most of the variables are highly associated with house prices. However, the type of floor, heating, and the roofs are less critical variables. And also the summarized model performance values, for example, are square prediction error. They provide a good matrices for evaluating the model performance. A big limitation of this research is we generate the distance layer variables based on the centroid of block groups, not the individual house locations, even though we found out a prominent spatial correlation in the house prices at individual house levels. And we would like to extend the kind of research by investigating the proposed proxying variables more with different data set or other machine learning algorithms. Thank you for listening to my presentation. If you have any question, please send me an email. Thank you.